Good afternoon, everybody. My name is David Gottfried, and I am the Deputy Director of the Coordinating Office for the NNCI, the National Nanotechnology Coordinated Infrastructure. And I want to welcome you to this, the first NNCI webinar, monthly webinar. We hope to, as I said, we hope to conduct these on a monthly basis, covering various topics of interest to NNCI staff and users, particularly in areas such as computation, societal and ethical implications, education and outreach, and innovation and entrepreneurship. Before we introduce today's speaker, before I hand it over to Azad Naimi to introduce today's speaker, I'll just mention that the next webinar will be held 3 weeks from tomorrow on Thursday, May 27th at 2 p.m. Eastern Time. And this will be a seminar in the innovation and entrepreneurship category, and will be given by Terence Barkhan, who is the Executive Director of the Graphene Council and the MXene Association. And the title of his talk will be 2D Advanced Materials and U.S. National Priorities. And you'll be seeing more information about that if you get our flyers or if you go onto the NNCI website at nnci.net. You can find more information about that as soon as it's available. So with that, I will sign off and hand it over to my colleague Azad Naimi to introduce today's speaker.
Thank you, David. Hello, everyone, and welcome to the first talk from a series of talks organized by the NNCI Coordinating Office. I am Azad Naimi, a professor of electrical and computer engineering at Georgia Tech. I serve as the associate director for computation for the NNCI. And as you know, the NNCI is the National Nanotechnology Coordinated Infrastructure. It's funded by the National Science Foundation, and it provides researchers from academia, industry, and government with access to user facilities with leading-edge fabrication and characterization tools, instrumentation, and expertise within all disciplines of nanoscale science and engineering. Now, modeling and simulation is a major and powerful tool for nanotechnology research, as it can guide experimental research. It can drastically reduce the number of trial and error iterations in experiments and enables more in-depth interpretation of the measured results. Now, to promote and enable wider use of modeling and simulations, we are starting these series of talks presented by world leaders in this area who can tell us about various modeling approaches, their strengths and weaknesses, and also what is possible now and what we can expect to have in the near future. Today, we are delighted to have our first distinguished speaker, Professor Dragica Vasileska from Arizona State University. And before I introduce her, just a reminder for attendees that if you have questions, you can type them in the Q&A box, and at the end of the talk, I will read them and our speaker will answer them. Professor Vasileska received her PhD from Arizona State University in 1995. She held a faculty research associate position within the Center of Solid-State Electronics at Arizona State University for 2 years, and then she joined the Faculty of Electrical Engineering at ASU. Her research interests include semiconductor device physics and semiconductor device modeling, with strong emphasis on quantum transport and Monte Carlo device simulations. Recently, she also is working on modeling metastability and reliability of solar cells. She has co-authored 3 books and 180 publications in prestigious scientific journals and over 200 conference proceeding refereed papers. She and her students have received numerous awards, including the 1998 NSF Career Award. And with this brief introduction, I ask her to start her presentation, and the title of her talk, as you see, is Simulation Software Next Door. Thank you. Please go ahead.
Thank you, Azad, for the introduction. I just want to say a few historical facts. This building here is called Old Main, and it was part of the Teachers College, on which grounds we have Arizona State University Tempe campus today. So I would like to start my talk with a quote from Richard Feynman's presentation, "There is plenty of room at the bottom," that was given at the American Physical Society meeting, which was held in Pasadena, California, in December 1959. And according to my knowledge, this is pretty much the first talk in which one can see discussion about scaling of the size of things and the introduction of nanotechnology. So the quote reads that what I have demonstrated is that there is a room that you can decrease the size of things in a practical way. I now want to show that there is plenty of room, and I will not now discuss how we're going to do it, but only what is possible in principle according to the laws of physics. And he finishes this quote with the saying that we have not done it, scaling of things so far, because we haven't gotten around it yet. And at that time, pretty revolutionary, which are not very far from today's reality, the Feynman predictions done back in 1959 were that to store Encyclopedia Britannica on the head of a pin, one needs a dot every 8 nanometers. To store all books in history, we need just a few yards squared. And if we code the text part and do 3D storage, then all books in history could be smaller than the sand dust, which he called a smart dust. And he reiterates that there is no physical principle that prohibits this. Let's go back to my talk. My talk outline is as follows. I will start with Moore's law, more, and beyond CMOS description. Then I will talk about the birth of technology for computer-aided design and computational electronics. I will next discuss challenges and solutions to Pcat, and I will finish my talk with a discussion on where one can look for a simulation software, and I will summarize at the end my talk. So let us start with Moore's law. Back in 1965, Gordon Moore was approached by the editors of a special issue of the Electronics Journal, and he was asked to make predictions on the development of technology. And Gordon Moore, looking at the current technology trends at that time, looked and put on paper the number of transistors as a function of year in microprocessors and draw a straight line, which later on became the famous Gordon-Moore law, which states that every 1.5 years complexity doubles. Now, the Gordon-Moore was revised back in 1975 that the complexity doubles every 2 years, but this was a little bit pessimistic because we know that from 1961 for over 50 years, the complexity has doubled every 18 months. To continue, the LG scaling path, transistor gate lengths has to be scaled into smaller and smaller dimensions. So what I'm showing on the figure of the left is the Dennard trends in orange for transistor scaling over the years. The symbols denote the experimental realizations of conventional planar transistors, and channel transistors are depicted with the open circles. Now, what is necessary to achieve scaling at the nanometer scale? It is necessary to use nanofins, mobility enhancement, conductive metals, tunable materials, and precision structure control. On the figure of the right, I'm depicting once again the scaling trends, the introduction of novel device structures, but at the same time, the use of more and more complicated fabrication processes. So we can see that initially the performance scaling was linear, but it's kind of getting into a saturation. And to overcome this saturation, new materials and devices are needed to continue the performance scaling. So what is the current roadmap for nanoelectronics? We have two avenues. On one hand, we have Moore's law and more, which deals with miniaturization. The second avenue is more than more, which deals with diversification. If we talk about system on a chip in addition to CPU contains GPU, memory, USB, power supply. So in other words, system on a chip today is a mini computer. With the advent of wearables and mobile communications, system in package became more important. And also it is very important with the introduction of artificial intelligence and smart electronics. Now, system in a package and system on a chip are currently being combined to get higher value systems which go beyond CMOS. So what is the traditional approach to device R&D? We start with the current technology for which we know the fabrication steps. We apply scaling laws and experience to get to the proposed next generation design. Then a prototype is being fabricated and its operation is characterized. If the desired performance is achieved, then we're done. If it is not, we have to go and characterize the prototype structure, in particular the doping profile, revise materials, fabrication process, apply scaling laws and our current understanding, and keep on going in this loop until we achieve the desired performance. Now, this is all very fine, but it actually becomes very expensive. So Pcat is considered today as a third mode of investigation in addition to theory and experiment. And while talking about Pcat, I would like to say some historical facts or perspective related to Pcat. It all started by the seminal work of Charfetergamal, with which they simulated large signal analysis of a silicon reed diode oscillator. And to analyze the operation of the silicon reed diode oscillator, they solved self-consistently the continuity equations and Poisson equation. And in these continuity equations, Jp and Jn are the current density expressions, which contain a drift and a diffusion component, therefore drift diffusion model. If one applies finite difference discretization to the drift diffusion model, we can get to the system of linear algebraic equations, which we have to solve simultaneously. Now, it is very important to note that when one applies finite difference discretization, for example, of the Poisson equation, it is explicitly assumed that the electrostatic potential varies linearly between mesh points. That assumption is pretty bad for the discretization of the hole and the electron continuity equations. So in this seminal work, Charfetergamal introduced what is today known as the Charfetergamal discretization scheme, which assumes exponential increase of the electron and hole densities between mesh points. Now, as I said, with the increased complexity of the production of nanoscale devices and their increased cost, it has become too large for any company or country to accept this increased cost for R&D. There is also a demand for shorter process technology life cycles, and there is also emphasis on faster characterization of manufacturing processes that can be assisted by modeling and simulation. So what are the benefits of modeling and simulation? We can evaluate what if scenarios very rapidly. Another thing is that we can provide problem diagnostics by providing full field, in-depth physical understanding on what is going on within the structure of interest. And all of this leads to decreasing the design cycle time and shortening the time to market. Pcat prerequisites are that modeling and simulation requires enormous technical depth and expertise, not only in simulation techniques, but also in fields such as physics, chemistry, material science, I would add mathematics, electrical engineering, etc. Now, in order for simulation modules to be practical, it is necessary to do verification of these models. So therefore, software and tool vendors have to be closely tied to development activities in the research and development laboratories. Things get further complicated in the nanoscale regime. For example, if we look at devices with channel lengths larger than 200 nanometers, we have classical transport, which is collision dominated. We call that diffusive transport. It is mobility limited, so mobility is a good figure of merit. Below 200 nanometers, velocity overshoot and one-dimensional quantum effects start to dominate the device behavior. Velocity overshoot effect is an effect in which the carrier velocity reaches values in the channel that are higher than the saturation velocity, and therefore the device exhibits small ballisticity. Below 100 nanometers, in addition to the velocity overshoot effect and 1D quantum effects, one also has to worry about dopant fluctuations. In other words, because of the stochastic nature of the process of ion implantation, we can have different number and different distribution of the impurity atoms in the active region of the device, which in turn can lead to fluctuation in the device, for example, threshold voltage, from device to device fabricated on the same chip. Below 20 nanometers, we have evidence, significant evidence of ballistic transport, two-dimensional quantum effects, and also the role of unintentional dopants can play significant role in, for example, affecting the magnitude of the on current, depending where we have those unintentional dopants. I would also like to say here that in the ballistic regime, transmission coefficient becomes a good figure of merit. Now, Purdue team has shown that scattering is still important in nanotransistors. So even any model that models nanotransistors has to take into account scattering. Now, as a special case of technology for computer-aided design is computational electronics, which focuses on primarily on three things, that is process simulation, device simulation, and some levels of circuit simulation. Of course, as I said, all of that has to be tied to experiments, which, for example, for the process simulation, would give the SIMS doping profiles or the TEM structure of the device. Process simulation gives the device geometry and the doping profiles into the device simulation module, which is verified by IVCV or for optical devices, quantum efficiency experimental data. And the device simulation leads to device electrical behavior characterization, which is next given to many levels of circuit simulation. If the circuit doesn't perform as we want it to perform, we go back to the process simulation, do the device simulation and circuit simulation until we achieve the desired performance. In terms of what consists process and device simulation, I would like to say, for example, in the process simulation, in other words, the process of diffusion, one has to solve Poisson's equation self-consistently with drift diffusion reaction equations that describe the chemical reactions happening within the structure. On the other hand, in terms of the device simulation, we have self-consistent solution of a Poisson equation with some transport model. We can characterize those into semi-classical and quantum models. The most popular models, semi-classical models in industry, have been for many years drift diffusion and hydrodynamic models. recently, with the advent of faster computers, Monte Carlo device solvers are gaining its popularity where applicable and where we need to worry about quantum effects such as collisional broadening of the states. Other effect would be the intercollisional field effect. We need to use quantum approaches. The one that is mostly used is the NEGF, which stands for non-equilibrium Green's function approach. At the smaller scale, we also need to use ab initio method. Now, the device simulation itself consists of several modules. For example, transport equation have to be fed by the electronic structure calculations and lattice dynamics calculations. The electronic structure calculations can, for example, be directly coupled to a Monte Carlo solver, and one can get what is known as a full band Monte Carlo device solver, or from the electronic structure calculations, one can extract the effective mobilities, the non-parabolicity factors, the band gaps, and use in conjunction with Monte Carlo solvers, non-parabolic device simulators. Now, these transport equations are consistently coupled with electromagnetic field solvers, and that is what comprises a device simulation platform. Here I want to talk a little bit more about the complexity and the computational cost of various PDE models for the electronic device simulation. As I said previously, we can separate them into classical models and quantum models, and in between we have the quantum corrected models, the simplest one of which is the density gradient. With moderate complexity, we have quantum energy balance or quantum hydrodynamic, and with high complexity, we have quantum Boltzmann equation. The classical models are as the ones I already discussed: drift diffusion, energy balance, which is a special case of a more general hydrodynamic model, and Boltzmann transport equation for direct solution of the Boltzmann equation. In terms of the quantum modeling, at the lowest level of sophistication, we have transfer matrix methods. Then we have density matrix and Wigner function, and most complicated are the NEGF methods for device simulations. If we're dealing with microwave or optoelectronic applications, we have to substitute Poisson's equation with Maxwell's equation. The range of validity of different methods is also illustrated in this slide, where again I'm reiterating the drift diffusion model is valid when we have many scattering events. Quantum hydrodynamic model can be used when we have rare scattering events, and Monte Carlo device simulations can also be utilized, for example, in modeling of nanowires, superlattices, and ballistic transistors. But if we go beyond these length scales, in other words, if we go to smaller length scales where the wave nature starts to dominate the device behavior, we either need to reside on direct solution of the many-body Schrödinger equation or the Green's function approaches. So let me now switch gears and talk a little bit about the challenges and the solutions to Pcat. I have extracted several examples which I think really represent challenges to Pcat, and they are in the focus of the scientific research. One of them is multi-scale modeling of gallium nitride device reliability. That involves different time scales, and it also involves different length scales. So for example, if we want to do Monte Carlo device level modeling, we need to supply to the finite volume strain calculation charge density and Joule heating terms, which can then be used to calculate the local strains and stresses using atomistic band structure calculations, which also provide band structure and the electron phonon, for example, matrix elements that are fed back into the Monte Carlo device level modeling. If we're interested in, for example, in a device and circuit level reliability modeling, we have to abandon Monte Carlo device model because we can do with Monte Carlo something in the range of a fraction of a nanosecond time scale. If we are interested in larger time scales, then bulk Monte Carlo results can provide the energy relaxation times, which are used in hydrodynamic device modeling, with which we can do milli or microsecond modeling. If we want to model transient trapping analysis, then we need to do reliability modeling. Now, the Monte Carlo kernel itself for modeling reliability of gallium nitride, for example, hence, is complicated as well, because these gallium nitride hens are used in power and RF applications in which one has to worry about short-range electron-electron interactions due to the high electron sheet densities. Gallium nitride is highly polar, so we have to worry about polarization effects and electromechanical coupling, which determines the piezoelectric polarization charge density. We also, near the source end of the channel, we have low field transport. We have to worry about quantum mechanical effects such as size quantization in the channel. And also, we have to worry about thermal effects, in other words, self-heating. Talking about self-heating, that is the second problem that I extracted because it is a big challenge to Pcat and multi-scale modeling. By nature, self-heating is multi-scale process because the wavelength of phonons is typically at the nanometer scale. The typical size of a phonon wave energy packet is tens of nanometers, whilst the phonon mean free path can be as long as microns. For example, in silicon at room temperature, the phonon mean free path is on the order of 300 nanometers. Now, what complicates things is that at different length scales, the phonons will interact with structures of different feature sizes, which can be as small as zero-dimensional defects. We talk in that case about point defects, short to medium range linear defects, which we call dislocations, medium to large range to the planar defects, which we call stacking faults and twin boundaries, and large scale 3D defects such as voids, inclusions, and various microstructures. What further complicates the multi-scale thermal transport is that different heat transfer physics is applicable across different line scales, and the physics that connects these different regions or scales is interdependent and it is coupled. Now, furthermore, phonon behavior is mode dependent, and therefore that complicates modeling and simulation very challenging. An example here is shown on the dominant role of interfacial heat transfer in thermal management of high-power electronics. This is a picture of the Blue Gene supercomputer stack, microprocessor as the hottest part of the electronics. And here we show the individual devices on the transistor and interface level in terms of, in other words, packaging and how heat goes from the device into the package. Another challenge to Pcat is modeling of ultra nanoscale transistors. I already talked about that we need new materials and devices to continue the performance scaling. And to study new materials, it is necessary to use ab initio calculations, which we will provide the proper band structure of the material from where we can extract the effective masses and the band gaps. It also provides the density of states function, which determines the strength of the scattering mechanisms within the device, and it also provides the scattering potentials or the matrix elements for the scattering mechanisms relevant for such material system. What are the challenges to Pcat? First principle calculations are very complicated. However, there are certain properties that can be calculated effectively with these ab initio calculations, such as electronic properties, structural properties, mechanical properties, dielectric, spectroscopic, and dynamical properties. What is hard to calculate is the transport properties such as thermal conductivity, electrical conductivity of semiconductors and isolators, and the diffusion. What is really difficult to calculate is the excited electronic states, which define the optical spectra. So if one is interested in using first principle ab initio calculations, one needs to get to an ab initio code, get an account on a supercomputer to run the experiments. Here I'm showing the list of top supercomputers, which is led by supercomputer Fugaku. Then we have Summit, Sierra, Sunway, Taihu, Light, etc. Now, back to the ultra nanoscale devices and memories, there have been also some solutions to Pcat. For example, the Purdue team has developed atomistic mode space approach for modeling of realistically large nanowire transistors, whereas the group from ETH in Zurich has coupled ab initio and NEGF calculations to model ReRAM. Now, where can we look for a simulation software? Let's start first with commercial Pcat tools. General purpose tools are Silvaco, Synopsys Pcat, COMSOL, Multiphysics, and Crosslight. Special purpose tools are Lumerical, which can be used for the design of photonic components, circuits, and systems, DST, which is electromagnetic field simulation software, and VASP, which stands for Vienna Ab Initio Simulation Package. Now, I have collaborated with Silvaco for over 20 years, so I was able to get some slides from them. And this first slide describes their new platform, Victory Pcat, that it consists of 3 general modules: process, device, and a circuit level module. The process simulation and the solid modeling has Victory Process and Victory Mesh modules. Victory Mesh does meshing and solid modeling. The device simulation includes Victory Device and Victory Atomistic, which allows nanoscale modeling. Now, to simulate semiconductor devices, and that is done within Silvaco and other Pcat tools, one has to start from small scale, feed these results from atomistic models into physical models, which then feed these results into geometric models. In terms of the process simulation solutions within Silvaco, there is a lot of development on the process of oxidation, stress, and strains, which are very important in ultra nanoscale devices, the process of epitaxy, etching, deposition, chemical, mechanical planarization, and patterning. In terms of the device simulation solutions, they have provided also software from atomistic to large scale, which can address modeling of displays, power devices, optical, radiation, advanced CMOS, and memory devices. I think this slide is very important, not just for Silvaco and other Pcat producers, but it is important in terms of knowing where the simulation is going. For example, currently the focus within Silvaco is on ReRAM support, atomistic quantum transport simulation. NeMo 5 is being integrated within the Silvaco simulation framework. In advanced emulation of stress, deformation, and physical etching is something that is also in the focus of interest. Visualization improvements are always good, and it is important to learn how to better model, for example, power devices, such as those fabricated in silicon carbide, like, for example, 4H silicon carbide, gallium nitride, gallium oxide, and diamond technologies. Machine learning is going to start to pick up, and we will see more Pcat powered by machine learning. New optical solvers are predicted, MRAM support, and what is also very important and is trendy at this point is the cryogenic support, so cryogenic temperature modeling. And that is, I would say, very hard problem from a computational viewpoint, because instead of the normal Maxwell-Boltzmann statistics that is applicable to most devices at room temperature, we have to deal with Fermi-Dirac statistics, quantum effects, and things are basically behaving very bad in terms of numerical convergence. The problem becomes mathematically ill conditions. We can also look for simulation software in the public domain, and one example of that is Nanohub. Nanohub was developed as a science gateway as part of the NSF-funded network for computational nanotechnology. It is being used by approximately 1.9 million annual visitors, out of which we typically have about 23,000 simulation users a year. Now, what made Nanohub so attractive? Rapture Toolkit. Rapture Toolkit was developed somewhere between 2006 and 2007, and what Rapture allowed, it allowed that high-end and non-user-friendly simulation software to be packaged within a nicely and user-friendly graphical user interface, which can then be used by non-experts. On this figure, you can see that the cumulative usage of tools that I have co-authored on Nanohub had started to have an exponential growth after the introduction of Rapture. Now, what does Nanohub provide in terms of simulation software? We can have access to ab initio free software such as ab init, Siesta, Espresso, molecular dynamics software such as nanomaterials, which does coarse-grained molecular dynamics, band structure lab as part of the band structure software, and in terms of the device transport models, we can have Pcat lab, which is run by basically the back end of this Pcat lab is the Padre drift diffusion software, Nanomos, which allows ballistic transport in nanoscale devices, Omen and its successor Nemo 5, which allow full band non-equilibrium Green's function modeling of nanotransistors. Here we have CNT FET and other non-standard simulation software, for example, for analytic spin precession simulation, nano heat flow, memristors, etc. There is also access to some circuit simulation software. But there are, of course, like with every software, there are deficiencies related to the Nanohub simulation software. The major deficiency, I would say, is the missing of the integration. In other words, the lack of a material library and the possibility of doing multi-scale simulation. In terms of the device modeling, more device simulation software is not developed and present at Nanohub. I wouldn't say that there is a missing link in terms of compact modeling, because the recent needs node essentially addresses this missing link regarding compact modeling. Other research tools one can find on tcatcentral.com software. And here we can get other publicly available software. You can look at this web page. You have access to software, websites, bibliography, anything you need to know about Pcat simulation. So in summary, I would like to say that computational electronics and Pcat in general is a third mode of investigation in addition to theory and experiments. The use of Pcat, both commercial and in a form of freely available user-friendly research tools, can reduce the cost and the time for development of new generation of nanoscale semiconductor devices. I would also like to stress that Pcat device modeling is at a very high level of sophistication, and process modeling is kind of catching up recently. However, more work is needed for further development of multi-scale Pcat modeling to address problems related to current and future state-of-the-art technology. When we talk about nanoscale devices, we always have to have in mind that parallel computing is a must. So with that, I will finish my presentation and acknowledge the financial support from the National Science Foundation, and thank you for your attention.
Thank you very much, Dragica. This was an excellent overview talk which covered many areas of modeling and simulation and gave us a lot of pointers for simulation resources. So we have one question, but I'm sure there will be more. So please feel free to write in the Q&A box, and I will ask them as they come in. So the first question is about the gallium nitride device. Can realistic defect structures be taken into account and related effects such as inhomogeneous heating caused by the defects?
There is some work in this area, but I would like to stress here, if I go back to this slide, that is a very hard computational problem because of the fact that it involves a variety of length scales. And defects by default are very difficult to treat. So I would say that there are some prospects of modeling these effects, but I would also say that they are at their infancy. For example, we have done modeling. I would like to add to that within our group at Arizona State University, we have done modeling of point defects in cadmium telluride solar cells, and modeling of grain boundaries is already a big problem. These are all 2D, 3D problems where you have you have to do conformal mapping, because as defects move, the interfaces changes, the structure of the defect changes. It is a very complicated problem.
And also about the inhomogeneous heating, is that something that can be accounted for?
Yes, inhomogeneous heating can be accounted if you couple, for example, we do it with a Monte Carlo simulation coupled with, for example, energy balance solvers for the acoustic and optical phonons that can take care of inhomogeneous heating at the device level. One has to also worry about a more global level, for example, how heat goes into the package and how heat dissipates through the contacts. But that is all possible, of course, with some level of accuracy.
Thank you. The next question is about the process simulation software and if there is any tool on Nanohub, for example, on etch modeling.
No. There is one of the deficiencies of Nanohub is that there is not a process modeling software. It's mainly device simulation software at the device compact modeling level. So that is kind of hard. And it's not, according to my knowledge, it still hasn't become part of the freeware that we can get on Nanohub.
Mm-hmm. So a follow-up question is, thank you. And if a graduate student wants to learn more about how to use one of the commercial tools, let's say Silvaco, what would be the best way? Classes, short courses, or something else?
I would say short courses. And as we were planning, Azad, we want to make a short course because that is an effective way of how to do simulation. It is not only to learn how to manipulate the software. It is very important to know what physics needs to be applied for a particular problem at hand. At ASU, for about 20 years now, I have been teaching a course on semiconductor device and process modeling, in which the main focus is on device modeling. But the first half of the course starts with transport and explains different transport models, which can later be invoked in a Pcat software. But you have to know which transport model to use based on the physical phenomena occurring within the device structure. So a short course would be a solution.
So actually, I had a question. So you talked about the challenges of modeling thermal transport, especially when you deal with phonons, and that becomes another multi-scale problem. It seems that the conditions over there somehow is similar to what we have for electronic transport, because if we have a very large device, drift diffusion models are enough, but once you go to smaller dimensions, then you need to deal with electron wave properties and scattering and those effects. Is there any, is it possible, or is there any effort to try to reuse some of the methods that have been developed for electronic transport and somehow apply to heat transport at nanoscale? Is it possible?
Yes, there has been several efforts for applying nanoscale transport to modeling of heat transport, for example, in nanoscale devices. One group that does that is the group of Matthew Louisier at ETH. Here at ASU, we have also worked on coupling, for example, Monte Carlo transport solvers with energy balance solvers for acoustic and optical phonons. There is also an effort at ASU going into coupling Monte Carlo solver for the electrons and phonon Monte Carlo solver, which is very formidable task, I would say. But you also have to worry about more globally in terms of the heat. Because as I said, in the phonon mean-free pad, in silicon at room temperature is about 300 nanometers. So we have to worry about the environment, where the heat is going, how the heat sinks, absorb that heat. So it is, I would say, a more multi-scale problem than it is like itself, the device simulation itself.
Interesting, very interesting. Okay, I think we are right on time for the end of this talk. Again, thank you so much for this excellent talk and a very nice and informative overview of modeling and simulation resources and approaches. And the presentation is recorded and is going to be posted on NNCI website. So we will keep an archive of all these videos online so people can also watch them later. Thank you again. Thank you, everyone. David, would you like to say anything? Or we are
just I'll echo you. Thank you to Dragica, and say thank you to our audience for sticking with us, and we'll see you at the next one.
Thank you for the opportunity to talk.
Bye all.